Tuesday again. So we don't have too much today. We got to go over the project 2 assignment, or no, I'm sorry, project 3, right? Our polynomial project, and then we want to talk about the final project today, and then we're going to talk about sorting and selection on Thursday, right? I think that was our plan, because that should probably just take us to one session. So let me pull up that in Canvas and fire up PyCharm here. We can start a new project. So how'd the polynomial project go for you using linked objects? So not a linked list, but the idea of having a link to follow. It's a little weird, but went okay? All right, cool. I know I had a couple questions the other night, but I think most everyone did pretty well. Let's take a look at linked objects. So we're going to write this inner class for term node. It's the idea that this is how we're storing all of the individual terms. This is our coefficient, this is our exponent, and then we have the next term in the chain. And then a polynomial knows what the first node is, and there might be more, might not be, right? And then you can add and multiply, differentiate, and integrate them together. You can turn it into a string, give yourself a nice looking string output here, and then if you equal or not equal another polynomial. That's what we're looking at for these ones. So we start up a new project. It's project 3. Now, there's a couple ways of going about it here. I think the easiest approach is figuring out how to add one term at a time. Because really, like, we take a big problem, we break it down into smaller and smaller and smaller problems. So taking two polynomials and adding together is taking one term at a time and adding them into that new polynomial result. So we talked a little bit about this idea that you don't take 2 and 3, add them together, and they don't change, you get a new result back out. So the existing polynomials don't change, we just build a new polynomial result that we're going to return when we're done. So we can write our class for polynomial, we can have our init, and inside of here, right, we can have that inner class for term node if we wanted, because no one else needs to use these terms, right? It's this belongs only inside of polynomial here. So with the term node, we can init one of these. The idea was that we needed to know the exponent and the coefficient, right? So probably we say coefficient first, coefficient and exponent. All right, I can never spell coefficient. Come on. Rename to, no, I can't spell. Do I have it here? Oh, 2 F's, right? Coefficient and exponent, great. And then we can have a self.coefficient equals the coefficient and a self.exponent equals the exponent. Now, because this is my inner class and I'm only using them here, I don't need to make them private and give all sorts of fancy ways of accessing them through public methods. We're just going to store some values. That's all these ones do here. And then we'll have a self.next here, right? This idea of the next probably could be none, or maybe we could have, exponent here. If you wanted, you could have a next starts as none, and then possibly you could give it one, right? So why not, right? We'll take next as whatever you tell me here. We'll assume it's probably none, but maybe if you know what comes next, we can set it. We might not use it. We'll figure that out as we get there. And then for term nodes, right? We needed to know if we equal or not equal another term node. Sure. So we can define our equals here. Do we equal another term node? So we can now checking ourself and the entire chain is a little tricky. If we just want to look at just does this term equal here, that's probably a little easier because polynomials are going to handle the idea of does polynomial equal another polynomial. So in terms of terms, I think just does my coefficient equal, does my exponent equal? It's probably the easiest one here. So we can just return my self dot coefficient equals the other dot coefficient, and my self dot exponent equals the other dot exponent. Right? Do the exponents and coefficients match? And then we're the equal, we're the same term here. And then for not equals, not equal, we're just going to return not self equals other, right? If we don't equal, we're not equal. So we just take the opposite of that. All right, so for polynomials, we also need a coefficient and an exponent here to make a polynomial. Right? This is our init here for polynomial. takes the coefficient, takes the exponent, right? If you didn't have term node take that, that's okay, but it's probably easier to do it this way. So we'll know what the first term is then, right? So we'll have this private first node. So this makes sense to be private. We don't need to expose the internal node to anyone else, right? We want this one to be private. So this will equal a term node, self.term node, given the coefficient and the exponent. That's my first term. Great. Now we exist, right? Then we can add, we can multiply, we can differentiate, we can integrate, we can string, we can equal, we can not equal. So we get to all those. So that's it for making a new one. So for adding then, so define add another one here. We need to take all of our terms, add them into a new polynomial, take all of the others terms, add them into a new polynomial. And if we do that one term at a time, it makes our life a little easier. So we can have a private helper method like add term that takes a, I don't know, term node or something to add. Sure, why not? So given a polynomial, you can add another term node to it here. So this way we'll add one at a time. And this is where the hard stuff happens. So ideally, we're going to take a polynomial. So this is the, I don't know, result equals a polynomial given my first term, right? So this is my self dot first node dot coefficient and my self dot first node dot exponent. So that's the start, right, for my result. So I'm going to copy my first one here. Here's my term's coefficient. Here's my term's exponent, because I know I have to have one. You can't init one of these without a coefficient and exponent. So I've got to have a first term. Then I'm going to go grab every other term and add it in. So I'm going to take my current term equals self dot first node dot next. Because if I have a next, we want to keep on going. So now while my current term is not none, we can take my result and we can call add term given the current term. Again, we haven't finished add term yet. We'll come back to this here, but the idea is take every term, add it in, and then my current term will equal the current term dot next, right? This idea of walking dot next. And go to the next one, go to the next one, go to the next one. Until we hit a none, just keep on going and adding them in. And then the same idea happens with the other. So add term needs a term, so it gets a little bit funny here, but we can take the other's first term and add it in, right? So we'll take my result, and then we're going to call add term given the other first term. And now we're accessing a private value here, but it's in the same class. This is usually fine here. We don't need to expose a get term method or anything. This makes sense here. So add all of our terms, at least our first one, and then anything else we have, and then we'll take their first term and all their other ones. So then I can say my current term is equal to other first term next. And really, it's the same loop here. Except now it is, current terms next. Exact same loop, but now we're working off of the others first term. We just go add them in. Again, we haven't done the add yet. This is where the hard stuff happens. But to add two polynomials together, take all my terms, take all their terms, add them together. We're done. So when this is finished, then we can return the result. Here's your new polynomial back. Bravo. Right? That makes sense for add? So all the hard work happens in add term, where we figure out if we have the same coefficients or we have the same exponents and add our coefficients together, figure out what the right order is, because they need to be in descending order when we store these things. It gets a little tricky here, but we can figure that out. So great. So for add term, so we first need to see if the term we're adding has a higher exponent than us, because it needs to go first, right? So, and we're going to slot it in anywhere as long as it is greater than the next terms. So this idea of if I have a list, a chain of exponents, of coefficients and exponents, here's my term, here's my term, here's my term, we'll find where it needs to go and put it in that spot, and then everything after it will fall into place. So whether or not it's first or in the middle, it's really kind of the same logic here. So we're going to have the current term is self dot first node, right? And we can say while my term node to add dot exponent is less than or equal to the current term, right? Because if we're greater than, we want to go in front. But if we're less than or equal to, we have to stop and think about what we're doing here, right? So if we are equal to, we'll do something. If we're less than, we just need to keep on walking, right? Because if we're less than, eventually we'll go after this thing here. So while this is true, right, if my current term dot exponent is equal to the term node to add dot exponent, oh, I named this badly here. Let me rename this here. Term node to add. There we go. That follows our format here. I think that's why I was yelling at me. So if our exponents are the same, then I can take the current term coefficient and just add the term node to add's coefficient, and then break the loop. This is a little ugly here. I generally don't like breaks, but I think this is okay for now. Right? I think that's okay. Yeah. Thank you. Exponent. Yeah, we want to check its exponent. And this needs to be also while the current term is not none. Right? And then my term node to add is less than or equal to. All right, so instead of breaking here we go. We can set current term equal to none. And then we don't have to use a break. This is probably silly, probably just as easy to use the break here, but I mean, whatever your preference is. Just if you want to not use breaks, that's okay. So if this is true, then we're done. Loop stops. Right? If that's not true, then my current term equals the current term next. Eventually, we'll find an exponent that matches, or current term will be none. Right? Because we went all the way to the end. Now the problem is, though, if we went all the way to the end, I can't set this term node to add to this current term's next. Right? Because the current term doesn't exist. It's a none. There is no next property, and I have to go back one. And we can't go back one if we only have the forward links. Right? There's no backwards. So what we're looking at is a little bit funky here. So we kind of want to be doing this off of the current terms next, so that we can set current terms next to this value. Does that make any sense? So like if current terms next is none, and we can even check that in here, right? So so while current term is not none, if we find a match, great. If it's not a match, then we want to walk really only if my current term next is not none. Then we can go to the next one. If it is none, then, right? And we know that we're less than or equal to, and we're not equal to, so we must be less than. I can set my current terms next to the term node to add. Right? This is so there are more terms to look at, and this is end of the polynomial. Term to add goes at the end. Does that make sense? I don't know if adding these notes is useful or helpful here. And maybe the break is better here, so I'll do that, because then you don't really need the else, right? Because if it broke, it's just done. And that way we save one indentation for what it's worth. It's a little prettier if stuff doesn't like get tabbed and tabbed and tabbed and tabbed and tabbed and tabbed. Just a style preference. Cool. So if it's not none, go to the next one. If it is none, then we're at the end. So we can add a single term, and this should add it in descending order, right? And it should combine like exponents. So if it's the first one, though, right, what happens if we do all of this, right, and we're not less than, right? Okay, so maybe what we also need here then, right, once we've added the term here, if we break, that ends the loop. Then you can add a loop else. Remember we talked about this way back when, last semester? So if the loop is broken, the else doesn't run. If it runs to the end, which is we evaluated the first one and we're not less than, well, this else will run, right? So loop ended without a break, which is essentially never ran, right? That's our case, is the loop never ran. Never ran. So else then, we'll set the self.first node I'm sorry, we take the current term, the term node to adds, next, set it to the self.first node, and then we'll take our self.first node, change it to the term node to add. Because we know we're only ever going to get a single term at a time here. We're not going to have to deal with a whole chain of terms. I don't care what it shouldn't have a next, because I'm only ever adding one at a time. This is my private method. I'm the one calling this one here. So I know you're only ever going to give me one term. I only care about the one term. Awesome. So we'll set its next to a value. We'll throw it in. Life is good. So let's add. I think that'll work. Yeah, we'll try it and see. So let's do the string result, right? So we'll define our string here. So we need to take every term, right, and put a nice. It's already in descending order. We don't have to do it. So another approach is, instead of putting them in descending order, you just put them any way you want. Finding matching exponents is harder at that point, but you can look through every chain, right? If it's an O of n operation, the more terms you have, the more exponents you have to look at, versus being descending order. Again, you have to look at a bunch of them anyway, so you could sort them before you turn them into strings if you wanted. I don't recommend that approach, but you could. So, and we're going to clean up anything that's to the 0 here, and we're going to round our coefficients to 2 decimal places. So we're going to have some sort of result here, is this, and then our current term will equal my self.first term, first node, right? And then while current term is not none, we're going to take our result and we're going to add to it here nice formatted string here. It's the current term's coefficient, and we want to round that, right? So to 0.2f, I think was how we round stuff. That was from last semester. I think that's probably how it's done. That is x to the, and then the exponent here. So my current term exponent, and then probably a space, right, to separate these things, right? Plus the next term in the chain here with some spaces. At the very end, when we're done, we'll have to trim off the last little bit here, and we can deal with that when we're done. We'll take current term, we'll walk it to the next one. Current term next, go to the next one. When we're done, we should have a nice long result string, but with a trailing plus here, so we could trim off those last 3 characters if we wanted. We could take result equals a slice to -3, just trim off the last 3 characters. Not very memory efficient, but again, for our purposes, we don't care too much. It's not too big of a deal. It'll make a copy, and that's okay. Result sliced. There we go. Then we can return result. Oh, here we go. Just return the slice. There we go. And save 1 line of code. Feel good about ourselves. So we should try it, right? See if we get out the results we want. Now, unit testing this is tricky. We can do it, but we're going to compare strings. That's okay, right? So we can do that. So let's go add a test. Let's go to, I didn't require tests. I want to make sure it works, and I'm going to use that unit test framework because that's how I like to do things. If you had a main method for testing it, great. If you didn't test it at all, how do you know it even worked, right? Like, you don't get points for the tests, but you get points for it working. I think was kind of the idea here. All right, so we're on to polynomial test add here. So we have from main import polynomial. Cool. So we'll make a first is a polynomial of, I don't know, 2 to the 3, and then a second is a polynomial of 3 to the 4, and then a result. So this is our range then. So we'll have an expected string. Expected string should be 3x to the 4th plus 2x to the 3rd, right, when we add them together, right? So then the result should be first plus second, and then the actual string is my result, or as a string of the result, and then we can self-dot start equals, I think that's right, equals expected string and the actual string. Oh, thank you. Yeah, because we had the 2 decimal places. Awesome. Let's give that a run. Oh, test add. Polynomial object has no attribute first term. Okay, well that's interesting. Do we must have messed something up here. So that was at Other first term. Is it not first term? What do we call it here? First node. There we go. First node, first node, first node, first node. Where did I call it? First term. Oops, this line here, right? First node, first node. There we go. This is what happens when type ahead doesn't work for you, right? Let's give that a try. Run it again. All right, let's see. It's failing here. Term node has no attribute coefficient. Current term, did I spell it wrong? Coefficient. Current term, coefficient. Right? I think I spelled it right. Coefficient. Term node. Term node. Coefficient exponent. What did I do wrong here? I'm not seeing it. Term node has no attribute coefficient. So it knows it's a term node. Knows it's the coefficient. I'm confused now.
Oh, the second.
Thank you. I zeroed on the first one. Thank you. I miss having type ahead work. All right, okay, now we're getting closer. So here we go. So 3x to the fourth plus 2x to the third does not equal 3x to the fourth plus 4x to the third. Uh-oh. Something got added here that shouldn't have been added, right? How did we get 4x to the third? Did I just typed it wrong, didn't I? No? 3x to the fourth, 2x to the third. Okay, so something's not working right. So let's try it and see. So let's put a breakpoint in here and run into debug mode. So we'll step into our code. All right, so we have self is 2x to the third, others 3x to the fourth. Looking good so far. So we'll make a new polynomial. Our current term should be our node's next. It is none, so it doesn't run. And then we get the other term's first node. So this is what we want to check to see. This add term here is probably where we're having trouble. So we want to step into here. So our self here is the term node. Goodness here, first node, 2x to the third. So current term will be us here. And then we're going to say, well, the current term's not none, and the term node to adds exponent is less than the current term's exponent. So current term's exponent is 3. The term node to adds exponent here should be 4. Okay, so this shouldn't run. We get to the else here. So the term node to adds next should be self first node. Okay, so then we have a next, and then the self first node should be the term node to add. Then we're going to add the, okay, so that one's done. Oh, we changed its, no, we didn't change the first node's next, did we? So current term will be the others first node's next. Oh, it has a next now because we changed its next. We took its term. Okay, so we didn't make a copy of these terms. So when we accepted the term and we changed the terms next, we did a bad thing. So I want then, instead of adding the others first node here, let's do this. So when you get a term, then we'll make a term node to add equals a self term node given the term node to adds coefficient, term node to adds exponent. This will make a copy of it here so that I'm not modifying the original. So we were modifying the term we were given. So we did a bad thing here. Does that make sense? All right, cool. So let's give that another run. I think now it'll be happier. There we go. Okay, so now that one passes. Cool. So let's go ahead again. Hi to my friend. Thank you so much for donating those bits to the Student Scholarship Fund here at the University of Michigan Dearborn College of Engineering and Computer Science. This is add more terms. Sure, why not? Because this is really the only way we can add polynomials is start adding them together. So let's add a third polynomial. How about 4x to the fifth? So we haven't combined exponents yet. We're just going to make sure that adding works for multiple length polynomials here. And let's do a fourth, right? Polynomial, how about 5x to the sixth? Right, so we should get 5.0x to the sixth plus 4.00x to the fifth plus, right? Plus second. Now, I think we can do plus third, plus fourth, because it should do the order of operations, right? First and second should get added, and then third should get added to that, fourth should get added to that, right? Just like it does with regular arithmetic, it just follows that order of operations. Let's see if this one works for us. All right, more terms seems to work. All right, so now let's try it with similar exponents here. So this is add more terms, same exponents. So if we have, where do you want to put it in? Probably doesn't matter too much the order, but let's try it here. So let's do the third and the fourth here. So we'll get two different additions that should add to the exponents here. So we should have 6 to the fourth. No, I'm sorry, 8 to the fourth and then 6 to the third. We have those together. Okay, let's give that a try. All right, and that seemed to work. So far, add feels pretty good, right? All right, awesome. So we did the string, so we can test it out. Equals and not equals. Define equals, given another here. So we want to loop through our first and their first, right? So we'll have our first, I don't know, our first or our current term equals self dot first node, and other current term equals the other dot first node, right? And now we want to keep on checking as long as they're both not none. If they're not none, then I can check their attributes. If one or the other becomes none, then when I try and access an attribute, it's going to crash on me because it won't have that attribute. So the loop has to be while our current term is not none and the other current term is not none, right? And something, right? Or really, we could just do it and they're not none. We can say, hey, if our current term dot coefficient does not equal the other current term dot coefficient, or the our current term dot exponent does not equal the other current term dot exponent. It's getting a little long here, sorry. Bump that down one.
Since you have the node not equal, then you just put that two nodes.
Yeah, there we go. Save some time. Thank you. So if our current term does not equal the other current term, return false. Thank you. I was doing too much work here. Right. So if we find a not match, stop. Return false. We're done. Otherwise, let's walk them. Right. We'll say our current term equals our current terms dot next, and the other current term equals the other current term dot next. If we get through the entire loop, we have a return false. We got to return true. But if one of these stops and becomes none, we can't just return true yet. So we can return our current term is none and the other current term is none. Right? If we've both got to none and we haven't returned false, we're good. If either one of those is not none, this will be false, and we're anding together, the whole thing will be false, we'll return a false. So it's just a shortcut here. Does that make sense on this one? I'm trying to save some code here. All right, cool. So we have equals, and then for not equals, again, we just take the shortcut here. Not equals, return not self equals other. Awesome. All right, so then multiply. Now multiply sounds like it's going to be hard, but it's actually really easy because we have add term. We'll define multiply, give it other. So it's our term multiplied by every other term, and then our next term multiplied by every other term, and then our next term multiplied by every other term, right? So it's our current term equals self dot first node here, right? And while our current term is not none, we're going to multiply and take this result. So now this one gets a little weird because the result starts as none. I can't just take my first term because it's really my first term times their first term. I don't want to have to do that twice here. So I'm going to cheat a little bit, and we can say the result equals none. And then in here, we can check to see if we need to add a term or we need to set the result to a new polynomial to start. I think that works because, let's see, otherwise we have to skip the very first one, right? And then you have to check if to know whether or not we're going to skip it inside the loop here, and that's a little bit annoying too. All right, so while our current term is not none, we'll say other current term is equal to the other dot first node. And while the other current term is not none, we need to do this multiplication thing. Now, I'm drawing a blank because it's been a while since I did math. We multiply the coefficients and add the exponents. Thank you. So we're going to create a term node, right? So this is a term to add. Will equal a self.term node, given my current term dot coefficient times the other current term coefficient. I can never spell coefficient. That's a hard word, right? So that'll be our coefficient, and then the exponent will be our current term exponent plus the other current term dot exponent, right? Add the exponents, multiply the coefficients. That's our term to add, right? And then if my result is none, then I have to do the special thing, and we'll say result equals a equals a polynomial given the term to adds coefficient and the term to adds exponent. Otherwise, we just take our result and we would call add term given the term to add. Right, so the special handling is this will be the first case. Otherwise, we just keep on adding terms. Right? And when we add terms, it manages keeps it in order, combines like exponents for us. We don't have to do any of that logic in the multiplication itself because it's already done in add to add a single term. Right? So we're going to leverage that work that we did. When we're done, we're going to return the result. Does this make sense? Oh, we got to make sure we walk our nodes. I forgot. So once we've done that, then our other current term equals the other current term dot next. And then when that one's done, then our current term will walk equals our current term dot next. Okay. Make sure that we don't have an infinite loop here. That would be sad. So for our first term times all of their terms, our next term times all of their terms, our third term times all of as many terms as we have is just two loops here, right? N squared or N and M or whatever you want to call them here, right? We'll return the result. So let's try multiply. So come over to test. Let's test multiply. Now let's just do a simple one to start, and then we'll try longer ones, right? So here's our test multiply. So 2x to the third times 3x to the fourth should give us, what, 6x to the seventh? And that's it, right? Coefficients multiplied, exponents added. Okay, let's try it. That one passed. All right, cool. So let's try one that's a little bit longer here. So let's try maybe a 2 and 2. Test, multiply. So let's like add two of these together here and then add these ones together. So, all right, my head's gonna hurt for a second here. So we want 2x to the third times 5x to the 6 plus 4x. So this one times this one, right? So if we take first plus second time, if we force our order of operations here, right? What do we get back out? So let's do the foiling here instead. So we have 5x to the 6th times 3x to the 4th. So we should have 15x to the 10th. Right, let's put this in here. Right, and then the next one here is going to be 5x to the 6th times 2x to the 3rd. So we get 10x to the 9th. Right, okay, then our next term here, 4 times 3 should be 12, plus 12x to the 9th. So we'll combine here. So this should be 22 then, x to the 9th, right, because those should get combined. Okay, so that one goes away, plus, and then 4x to the 5th times 2x to the 3rd should be 8x to the 8th. Did we do that right? All right. I've not had to multiply polynomials in a long time. All right, let's try it. See if it works. It worked. I am like, oh, it says this. Okay, it's not equal. It's just equal. Oops, equal. I was getting that warning every time. My bad. Okay, give them a try. Let's run those again. All right, and they pass. Awesome. So back to polynomial. So now we need differentiate and integrate. Okay. Now I think we said with these ones here, we're going to return a polynomial result. So we're not going to change our original. Is that what I said? I can't remember. If you change the original because you didn't remember what I said, that's okay. But ideally, again, it's like we're making a new result back out here. So to differentiate, let's find differentiate. That's probably close, right? So we're going to make a result and then keep on adding terms. Right? So then my result equals a polynomial given my self.firstNode.coefficient. And when we differentiate, we're going to take our exponent down by 1 and multiply the coefficient by that. Right? So do you subtract 1 first? I'm trying to remember now. Times the exponent. Okay, that's the other one. So times self term node first node dot exponent, and then its exponent will be self first node's exponent minus 1. That's the first one. And then our current node is going to equal the self dot first node's next. And while my current node is not none, we're going to take the result and we're going to call add a term given the current node's coefficient times the current node's exponent, and then its exponent will be the current node's exponent minus 1. And then we'll walk that current node. Current node equals current node dot next, and we'll return the result. Right, so we've got the same logic here twice. I feel a little bad about it, but I don't know how. Sure, maybe we could add a little helper method or something here if we wanted, but you could give it a node and they'll give you back another node, or I don't know. We could differentiate one node at a time maybe, but I don't feel too bad. Only a little bit bad here. Okay, so if we differentiate, we should be good. Oh, we forgot in our string here to deal with when exponent was 0. Right, so this is if my current terms dot exponent does not equal 0, then we'll do this, right? Otherwise, we're just going to take the, oh my goodness, it goes to 1, right? So it's just the coefficient, result plus equals coefficient. And this one, right? It just drops the exponent if it's 0. Okay, should be okay. We didn't need to do any of the other fancy stuff, worry about any of the other exponent values. Okay. All right, so when we differentiate then, let's make a test for differentiate. Let's just take one of these, I guess. Test differentiate. So 2x to the third plus 3x to the fourth differentiated should be 12x to the third plus 6x to the second, right? Result equals result of differentiate, and then get the string of that. Or we could take all of this, right, first plus second, and then call differentiate, right, save us one line. Just so we have something longer to deal with, I don't know, to test a little bit longer. Let's see if that works for us. Uh-oh. Let's see. Add term. Oh, I forgot. So this is a self.term node given these values. Node. I tried to pass it 2 values here. So we need to make a term node then to add given these values here. Right? Make a new term out of those values and then add that term. All right, try that. All right, it passes. Awesome. So then integrate. Integrate. So same idea here, but we're going to do it in reverse. So it'll be the coefficient divided by the exponent plus 1. Order of operations. And then the coefficient exponent plus 1. Right? So divided by plus 1 and then plus 1. And go to the next one. 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 I think I said we can ignore trying to do this with bad things if we have 0. Like if your exponent was -1, don't worry about that. I think I said, right? We could do some checking for it, but then it gets kind of messy anyway. So I think we're probably okay. All right, so let's test integrate. Integrate. All right, so 2x to the third, 3x to the fourth, plus 2x to the third integrated then should give us, these numbers aren't very good, are they? So 3 divided by 5, that's 0.6, 60, right? X to the fifth, that would be 3 divided by 5, and then 2 divided by 4 would be 0.5, x to the third, I think, if we integrate. That seem reasonable? So 3x to the fourth integrated would be 3 divided by 5, and then 2x to the third integrated would be 2 divided by 4 to the 4. Okay, I think that's right. Let's try it and see. Oh, goodness. Okay, so we get, with a leading 0. Okay, leading zeros. Is that our problem? Nope. X to the fourth, thank you. That's right, because we integrated. Yep, we went up 1. We're getting there. We're getting there. All right, awesome. That worked. I got 36% battery left. We're looking good. We'll make it. All right. Anything else for the project then? I said unit tests, but this was like, I think my example? Because I didn't put any points for unit tests. I don't know why I said unit tests here. I'm confused now. Sure. Maybe that was just the examples here. Oh, we could have tried these too. Oh, that's fine. So we have terminal class, we have the add, we have the multiply, we have differentiate, we have integrate, we have the string, we have equals and not equals. All right, so I feel like we've covered our bases here. We got all of our polynomials done. Did you guys do it the same way, different way, similar? Cool. There's one, not this one here. I don't know what that is. Oh, I need mine. My goodness. There we go. Project 3. No, you don't want any of this test stuff. Just playing around, forgot to delete it. Okay, project 3. I'll just discard all that test stuff. There we go. All right, so we got to talk about the final project. I know you folks are excited, right? You don't sound excited. Sorry. End of term's coming up soon, isn't it? Got a lot going on. So here's CIS 2001, 3, final project. Now, you folks have taken some stats, right? Some stats? A lot of stats? No stats? Some stats? Some? Okay. If I mention Monte Carlo in terms of statistics, a Monte Carlo analysis, does that ring any bells? Okay. It's not too bad, actually, I promise. So Monte Carlo analysis. This first link, ukindeed.com? Don't love that one. Monte Carlo method. Okay, Wikipedia. They're probably better. It's a broad class of computational algorithms that rely on repeated random sampling to obtain numerical results. The idea is that we're drawing from a probability distribution. I don't want to do all gazillion possibilities and give you an exact result. So I'll take a tenth of the gazillion possibilities, and if we've sampled randomly, it'll probably be pretty close to what the actual results were. It's a little bit of hand waving. Again, go talk to your stats prof here. I can't give you all the math to back it up, but for our purposes here, we can use this approach to not do as much work when we do our simulations, because some things are hard to solve mathematically. Right? Have you folks played poker before? Okay. Yes, no, you're going to hate this. I'm sorry. It's interesting. You might like it. If you played poker before, it might be interesting. So there's a variant of poker called Texas Hold'em. Texas Hold'em. And this is a pretty popular variant of poker. Has all sorts of interesting odds and statistics, and I think that's why people tend to like it. The idea with Texas Hold'em is every person at the table gets 2 cards. Those are your 2 private cards. And then what happens is over a series of turns, and people get to place bets and all sorts of other silly stuff here that relates to poker, you build out a set of community cards in the center that anyone can use. Eventually you'll get to 5 of them. So with your 2 cards and the 5 cards in the middle, the goal is to build the best possible 5-card poker hand. So if you look at poker hands here on Wikipedia, it's the best possible poker hand, ignore 5 of a kind because there are no jokers in legitimate poker, is a straight flush. All the cards are the same suit and they're in numerical order. That's the best possible hand you can have. The next best possible hand you can have is 4 of a kind, 4 cards that are the same. Now, 2 different hands could have a 4 of a kind, but then their 5th card would determine which is actually the best. So whoever has the highest 5th card then wins. So it's possible in the 5 shared cards in the middle, you have 4 of a kind, but then someone in their 2-card hand, their private cards, has a higher other card, 5th card to use, right? And that would make a better, best possible poker hand. And you just work your way down. So they all kind of tie break a little bit differently. So the straight flush, the highest starting card is the best hand, right? With a full house, the higher 3 of a kind is best, but if you both have the same 3 of a kind, then your higher pair determines who is the best hand. And again, it's possible to tie with any of these here. A flush is all the cards of the same suit. A straight is they're all in numerical order, right? You combine those 2 to get the straight flush. 3 of a kind is just any 3 cards are the same. They tie break based on your 4th card or the 5th card if those ones match, right? So you look at your 4th highest card, or your 4th card, which one is higher, or then your 5th card, which one is higher. Where you determine those 2 pair, which is the higher pair. If that first pair is the same, which is the high second pair. If that pair is the same, which is the last card. A single pair, and then all the other 3 cards, or just who has the highest card. Right? Some you can go that way. So it kind of walks you through how you tie break each of these here. So what happens then in Texas Hold'em? Let me do our assignment here. So this is, I'm sorry. So you get 2 cards and there's 5 in the middle. So we're going to do 7 cards combination 5. So 7 combination 5 gives you 21 possible poker hands because the order doesn't matter here, right? It's not permutations, it's just combinations. So 7C5 gives us 21 possible poker hands. We could build out of a given 2-card Texas Hold'em hand with 5 shared cards, right? So this is the final project. Texas Hold'em odds. Oops, I want my classroom link here. URL to your repo and a self-assessment and a partner assessment. Right? We're going to work together on this because that is an outcome for the class. Right? Learn how to work together. I promise you, sometimes it's hard, but it's definitely worth it, and it's really lonely to program all by yourself. So hopefully you've got the opportunity in the future to work on a team on things because you'll get better results and it's much more enjoyable. Even if all of us programmer type fit that antisocial role, it's okay. People aren't too scary. All right, so this is our Texas Hold'em odds. So we're going to use the Monte Carlo method. So using the Carlo method, this is the Texas Hold'em link. We're going to display odds of winning a 1v1 Texas Hold'em game versus a computer. So generally with poker, there's a large table of players. That makes things a lot harder for us. So we're just going to have 1 player and 1 computer. So just I get 2 cards, they get 2 cards. Eventually we'll build up those 5 shared ones in the middle here. Okay, so here's the poker hands, poker hand ranks. Okay. So when we start the game here, it's done in start 4 rounds of play. So the first round, player and computer each get 2 cards. There are no shared cards. Okay, so in every round there's a chance to bet. So you can say, hey, I want to bet X amount of money. And there's all sorts of other rules and variants around how much you can bet and maxes and things like that. But we don't need to do anything too complex. So you can bet, and then the other person has a chance to either call your bet, say, okay, I will match that amount. I want to see the next cards. Or we're going to skip this part. They could raise and say, okay, I want to bet even more. We're going to forget that because that just makes life harder. So we're just going to let the player bet, and then the computer will respond. It'll always be the player betting. It'll always be the computer responding because that makes life easy. It's not how the real game works, but that's okay. So our simple version always has the player bet first, and the computer will either fold or call. A royal flush isn't a thing, Kylie. It's royal flush is just a ace, king, queen, jack, straight flush. So it's not any different than a straight flush. So it has a special name, but it's not a different hand. It's just a straight flush. So it's the ace high. So aces count as high in here, not low, but they technically can be low for straights. You can have ace 2, 3, 4, 5. Don't worry about that. Just forget the ace low straight. Just pretend it's always the high card. So ace, king, queen, jack, ace, king, queen, jack, 10. There we go. Will be your 5-card straight. Does that make sense? So again, focusing mostly easy here, trying to take out some of these. So the player will always bet first, and the computer will either fold or call. So the player has the option to bet 0. 0 is an option. It's technically known as a check. It doesn't matter. So you can bet 0, and then the computer will just always call, right? So bet 0, computer should always call. So if it's a 0, the computer won't fold. Either call or fold. It has a 50% or better chance of winning. It will call. Otherwise, it folds. So we need to be able to figure out what our odds of winning are. So in the very first round, when I have 2 cards, there are 50 cards that I don't know about, right? Of those 50 cards, 5 of them will become shared cards. 2 of them will become my opponent's cards. So I think Wolfram Alpha does this better than just trying to search here. So 50 combination 5 at a time means that there are 2,118,760 possible 5 shared card combinations, right? For what the 5 possible cards are out there. So when I have to figure out what are my odds of winning, I need to, for each possible 5-card combination, what happens, right? Then once I know what my 2 cards are and what the 5 shared cards are, that leaves 45 cards left, right? So 45 combination 2 is how many possible hands can my opponent have? Well, there's 990 of those. So of the 2 million possible 5 shared cards, each of those then has 990 possible opponent hands. I don't want to do 990 times, what is it, some million, right? I should have kept that in another tab here because I forgot already. Let's go back one. There we go. So 2 million times 990. Right? That's not too big of a number here, right? So what's 2118760 times 990? So it's 2 billion possibilities to compute. I don't want to compute 2 billion possibilities, right? I mean, we can do it. It'll happen. It'll just be a little slow, right? So what if we did like 1% of that? Can we compute 2 million possibilities? We could probably do that, right? And if we get a good random sampling, this Monte Carlo method says that's a pretty good approximation for what the actual results should be. It's not going to be perfect because it's just a random sample, but we take a large enough random sample of a good, evenly distributed sample set, which it's completely random. Like doing this in the real world when you don't have actual random, evenly distributed data is tricky, right? Because if you get real data doesn't always randomly distribute, that sort of thing. Again, that's more of a stats thing, so that's fine. So with no share cards. So 2 cards, so there's like a bunch of possible outcomes here. Possible combinations of 5 shared cards and 2 opponent cards. right? And we add in those commas here. I wish the calculator did that for me, right? So maybe 1% is a good size to sample. And again, this we can change this. We can tweak this here. Like you can start even smaller. Just do let's just do like 0.1%. Let's just do 100,000 or 200,000 because that'll be even faster for you. If you're always running the slow thing every single time, you're going to be really frustrated because it's going to take a while. So as we're like testing and debugging and playing with it, feel free to use small samples. Right? You can use the small ones as we're playing, and that's okay. Right? So after the first round, so if the computer does not fold, then we get second round. So at the start of the second round, 3 cards are put in the shared pile, shared pool, or I don't know, 3 community cards. I don't know how to say that, right? 3 cards are revealed in the center, right? So now I know my 2 plus 3, there's 47 left, right? So now I have 47 combination 2, because there's 2 more cards that'll be coming out being added to those 3, right? So that's 47 C2. This is 1081. So there's 1,081 possible 5 shared card combinations now because I know 3 of them. 3 are fixed. What's left? How many other ways can I make those 2 cards, right? So this is a lot less now all of a sudden, which is much nicer. So it's easier to do this sort of analysis here. So this is 1,081. 1,081 possible 5 shared card combinations now. All right, I think we should have, let's see, this was 2 million. Why can't I highlight that? 211. It's 118,760. 118,760 possible 5 card, 5 shared card combinations, and 990 possible 2 card opponent hands for each of those, right? So that gives us that grand total here. So this one's not so bad now, right? So that's 1,081 times 990. So the 990 is never going to change because it's always 45 cards we don't know, right? 990 possible opponent hands. That's only 1 million. But again, we could do a subset of that. We could take a random sampling of those to figure out what our possible odds of winning are here, right? Possible combinations total, right? Making sense so far? Again, it's a lot if you've never played before. I'm sorry. We'll get to it here. Okay. So what we need to be able to do is to figure out, of all of these possibilities, do I win, lose, or draw? Right. So I need to be able to take a hold'em hand, which is 2 cards and 5 shared cards, find the best possible 5-card poker hand, which is 21 possible poker hands, find the best one of those poker hands, compare it to of all the possible hands I've generated for them, their best 5-card poker hand, and see, do we win, do we lose, or do we draw? So we need to be able to compare poker hands to see, do we win, lose, or draw? We need to be able to compare hold'em hands to see, does my hand beat their hand, win their hand, lose their hand? And that uses the poker hand logic for that. And we need to generate the best of 21. And if one poker hand compares itself to another poker hand, I can generate my 21 and see which one's the best from my 2 cards, 5 shared cards. And then with the computer's 2 cards, 5 shared cards, right, as I'm doing these possibilities here, get their best hand of 21 possible hands, and then compare my best with their best. Do we win, lose, or draw? So we're going to keep a count of win, loss, or draw here, and we can display the odds. So we're going to display odds of winning player, and the computer is still going to use those odds to determine whether or not it should fold or not. Again, this 50% is not really a great metric, and there's all sorts of other things that go into actual poker playing, but it's going to say, hey, if the odds look like we can win, let's go for it, right? It's not exactly how it all works, but that's okay. So then the third round, right? Third round, again, if the computer doesn't fold, we get a third round. As soon as the computer folds, the player just wins. Right, so the third round, a 4th shared card is placed. out. Fourth card is put in the shared pool. Right. So now I know what 4 cards are. So there are 46 left, one at a time. There's only 46 possible 5-card combinations now. Right? That math is pretty easy because there's just 46 cards that I don't know. 46 possible 5 shared card combinations. For each of those, right, there's still 990 possible opponent hands. Right, so 46 times 990 then, 46 times 990 is only 45,000 possible combinations total. Right, another round of betting. And then the 4th round, 5th card is put in the shared pool. Now we know what it is, it's fixed. Now there's only the 990 possible opponent hands we could have. 90 possible opponent hands, and that's the only possibility now. So the amount of calculations we have to do gets smaller and smaller and smaller. And in real life, this is all like saved in the database somewhere. They don't actually compute it anywhere. They just go look it up. We don't know how to do that yet, so that's okay. And we can take advantage of some of these computational approaches and say, let's figure it out. So you bet again. If the computer calls, then you actually see who wins. And all of the money that was bet goes to the winner. If you draw, you just get your money back. Or in this case, because it's only 2 people, you split it evenly. If in the real game there are 10 people playing and a couple of people play a round and then they end the second round, then they fold, right? It's not an even split, but it's more complex than we need here, right? So we're going to track the player's money and the computer's money. Start the player and computer with 100 each. Don't allow the player to bet more than the computer has. Right? So if the computer's down to $50, you can't bet $70, right? Because they can't call. It's not possible. And there's rules in poker and all sorts of other fun stuff there. But this is the idea. We'll do some odds, do some statistics, tracking all of these things, holding all these possible values in memory and comparing them. Right? We want to look at how efficiently we're storing these things. How do we want to put them in memory? Right? Do we even need to keep them in memory? There's all sorts of interesting options here, right? Because as we keep playing here, right, depending on what we've done, right, of those 2 million possibilities, these 1,081 are contained within these, right? We've got some of them, but not all of these will have the 3 cards. So we'll have to throw away some of them at least that didn't match. And depending on how large of a sample size we took, we might have none. Right? I might not have any of these of the 1% that I did that had the same 3 cards. There's just a chance of that, right? So, but if we wanted to keep it in memory and then see if they matched, right, there's less computations we have to do later. It's just an option. So some trade-offs to think about. Memory is pretty cheap. 2 million hands doesn't actually take up a lot of space. It's just 5 cards. 5 cards have a suit and a value. Right? It doesn't take up tons and tons and tons of memory, but you don't want to keep 2 billion of them around, right? Like that's probably pretty rough. Again, doable, right? Computers have a lot of memory, modern computers do, but it'll just take a while. So some things to think about. This is our final project here. So this is, oh my goodness, I don't even remember how many points this was. 40 points. There we go. 40 points. So I'll draft up a rubric. I'm almost out of battery here. What do I have? Oh, I got 22.3% left. So 25% of your score comes from being a good partner. It feels like a lot, but that's the goal, right? You want to be working with somebody, being a good partner here. So when we put the rubric together, the peer review, the peer, like how well did my partner do, makes up a good chunk of your score. Not all of it, but a good chunk of it. Now, if your partner has done absolutely nothing, please don't wait until the presentation day and tell me your partner did nothing. Right? That's not good. Right? You need to be communicating with them early. That's why we're starting early. If they're not hitting the deadlines, okay, you're doing this part, I'm doing this part, and they're not hitting the deadlines, you need to let them know they suck, right? You didn't meet the deadline. You need to do it, or I don't know, because you're not going to get your partner's score if you did nothing, right? If you did a little bit, then you might not get very much in the partner eval, right? But you contributed a little bit, and it's kind of a sliding scale. But if you screw your partner over, you get no points. You fail the project, and if you fail the project, you can't pass the class, right? Without these 40%, right? Where does that land us on our letter scale? But it's not even in here, right? Because that's the standard, right? If you don't finish the final project, you don't pass, and that's sort of the goal here, right? This is the culmination of all the things that we've done so far with our intro to computer science. Putting it all together here, looking at some of these things. Again, we're not using recursion. We've talked about it, but we don't need to use recursion for this project. It's not appropriate, so it's not for everything. But we'll look at how we're storing our data and have some fun here. All right, so I'll add that. Let me publish this, and then I can add the rubric after. So we get, this is our final project. So this is our eval is 10 points. Okay, and then now thus far I've not asked for anything specific in terms of committing to GitHub, like just turn it in, we're great. Because this is the large project worth a lot of points here, and I don't want you to just go copy paste a solution from online, the goal is we build it iteratively. So there'll be points here for committing chunks of work almost every week, right? So the commits, I don't know, frequent commits, something frequent commits showing progress. So 10 points, essentially a point per commit. So at least 10 commits over the span of the 4 weeks. And beyond that, great, right? But you have to at least chunk it out into smaller pieces here. So this is like 1 point per commit up to 10 over the 4 weeks. Right? If you do them all in the last week, not great. If you do them all the last day, there's no points here, right? You just can't commit it all at once. And then, like, the idea is that you're working on it slowly, building it out. It's all right. Like solving which poker hand is better than another is not an interesting problem to solve. Go ask the chatbot. That's fine. Cite your source. Hey, I asked the chatbot. Now, do you know if it gave you good code? Right? How do we know? So if you use the code that it gives you, you need to verify that it actually does what it's supposed to do. That's the idea. We need to have that expertise to say, did it do it right? Because it sometimes will give you garbage code. Right? There's all sorts of interesting Twitter threads around it being very confident that it gave you the right answer and it was wrong, which is, it's interesting as we sort of lean into this sort of stuff here. All right, so frequent commits showing progress. So points for being a good partner, points for at least committing your work. You can get 20 out of 40 points, even if it doesn't work, that you just tried and were a good partner. Now, you probably weren't going to be a good partner if the project didn't get finished. Right, so like you probably won't get all the partner points if your team didn't get it done here. And then this is our Monte Carlo analysis showing odds. We'll do 10 points for that. This is for each round, and then the gameplay and money tracking is 10 more points. So even if we don't do any analysis, you can still get some points just that you can play the game. Right? You'll have the computer play even if the odds are faked. Actually getting the odds in here, right? That's how we'll actually get an A in the class, right? You can pass the class without doing this. That's okay. It's up to you. But like to get the A, you've got to do all of these things. Does that make sense? All right. So I'll add that rubric. So that's what we have on tap for the next 4 weeks. Again, sorting and selection probably won't take the whole time. So you can get with your partner and start working. Ethics will probably just take 1 day of those 2. So we'll probably actually have 4 sessions for project work time for you to work together. I'm happy to answer questions, float around the room, help you out, get you pointed in the right direction, and we can go from there. Does that sound reasonable? I want you to be able to get it done. And then hopefully if it's done by 418, you've got no stress for the final for this class and you can focus on your other ones. All we have to do is show up on April 25th and you just show us that it works. You'll run it. And we'll play a couple hands and we'll have some fun. And then we'll look at everybody's code to see how everyone did it a little bit differently, which is an interesting piece. Like there's not just one right way to solve a problem. Lots of different ways we can solve the problem. Now, one might be the most efficient way, and that is arguably probably the best way. But I might also say if you can actually understand and read the code, that's a value too. Because if you come up with like a one-liner that no one understands because you figure out the math somewhere, I mean, what good is that? So, all right. Any other questions, thoughts, concerns? Cool. So we are wrapping up March. We've got one more session in March, and then we've got April, and we are well into the end of the winter semester. So it's been fun, and I'll see you Thursday. Thanks for hanging out online, folks.